MLF3. This is now our topic. Performance test of many hydroelectric power plant. So parang matadoble lang yung names natin dito sa power plant. Diba? Power plant design subject natin. So the many hydroelectric power plant. Ito yun. Micro hydro turbine installation. Maliliit. So natin kung may ilog ka, river, tapos gusto mo magkaroon ng power plant, tayo penstock, which is the micro hydro turbine, ikot siya to produce ng power. Okay? So, punta doon sa kabilang side na ilog. Yeah. So, how a small hydroelectric plant works? So, based dito, visualize nyo, pipe, pasok doon, tapos sa turbine. Okay? So, a small hydroelectric plant does not always require tall waterfalls and large quantities of water. In addition to water drop plants, there can also be some small running water hydroelectric plants, which exploits the flow of water instead of the power generated from the drop. Only. The small hydroelectric plant exploit the kinetic energy related to movement of streams and rivers. Water is collected via intakes and conveyed to channels or pipes to a charge basin where the upper free surface needed to calculate the drop required by the small hydroelectric plant is determined. At this point onward, water reaches the turbine by means of penstock and its passage through the moving parts, also known as impellers, produce rotation. Then the impeller shaft is connected to an alternator that generates electricity. The water leaving the turbine is released by means of the restitution works into its original channel at a level which determined by the lower free surface. What is the composition of a small hydroelectric plant? A small hydroelectric plant is made up of civil and hydraulic components. So intake works. This changes the configuration according to the type of water course used in the orography of the area. Filtering works. This serves to remove large suspended bodies from the water, and the type of work depends on the amount of water involved and the type of solid in the water. Conveying works. This consists of channel or penstock depending on the orography and consequently the type of plant with a low or high water drop. Restitution works. This channel the water back to the main water course. Okay. Classification of mini hydro power plants. So the term mini hydro power plant refers to plants with a capacity below 10 megawatts, according to UNIDO, United Nations Industrial Development Organization. Classification. Its modest size helps to reduce pressure and environmental impact. Many hydropower plants are classified as follows. Meron tayong pico plant. So the power is less than 5 kilowatt. Micro plants, the power is less than 100 kilowatt. Mini plants, less than 1,000 kilowatt, maliliit. Small plants, less than 10,000 kilowatt. These are called the mini hydro. So generally speaking, this classification is valid worldwide. Okay. Another way of classifying mini hydropower plant is based on their functioning in relation to the method of water intake and storage. Flowing water facilities. These do not have the ability to be regulated. Capacity during the year depends on the hydrological regimen of the water course. The amount of energy produced is strongly influenced by the capacity of the water course. Okay? This also represents the main limitation of this type of the facility. as the production of electricity depends on the capacity of the watercourse that can be exploited. So it is a design based on the usage, which by definition is variable throughout the year, resulting in variable levels of production according to the season. As can be imagined, for example, there is a greater production of energy in the rainy season. Ah, regulated flow facilities, storage. Ah, this can regulate water flow using daily, weekly, or monthly regulation tank. Regulation is linked to the tank's storage capacity. They exploit the potential energy contained in the water collected in natural or artificial basin. The amount of energy produced depends mainly on the drop. Next is many hydropower plants are usually water flow facilities built next to rivers, streams, or irrigation canal with a constant speed in relation to the in-stream flow as an index of maximum decrease in the flow of our water course downstream from the intake system that's required to protect the ecosystem. Another way of classifying, oops, okay, wait, ulit na. So, okay, yung mga classification. Now, for the equations, hydraulic equations, again, fluid machinery nyo. The horsepower required by a hydraulic turbine may be calculated by deriving an equation based on the definition of horsepower, which is 33,000 foot-pounds per minute or 550 foot-pounds per second. So P is equal to Q H Z gamma N sub T over 550. P is the turbine output. Q water flow rate. H sub N is the net effective head. Gamma is the water density. N is the turbine hydraulic efficiency. Tagalin ko lang to. Now, taking the water density as 2.4 pounds per cubic foot, so P is equal to QH sub N sub T over 8.82. The term net effective head is defined yung H sub N as the difference in the total head for the water entering the turbine casing in the total head leaving the duct tube. For the moment, it will be sufficient. For the moment, it will be sufficient to indicate that the duct tube is a conduit at the outlet of the turbine that conducts the water away from the turbine. Net effective head, as defined, may be determined by the ducting losses in the intake canal or intake conduit from the difference in elevation between the storage reservoir and tail race. The tail race is the canal that is used to carry the water away from the plant. So for a turbine, specific head speed may be defined as the speed of a hypothetical model turbine having the same configuration as the actual turbine, when the model would be of the proper size to develop 1 horsepower at a head of 1 foot. Note that the definition of the specific speed for a turbine is in terms of horsepower and head, whereas for the pump it is in terms of low, low in terms of flow and head. Okay, okay. Low, low yan. So equation 3, n sub s equal to n p exponent 1 half over s sub s exponent 5 over 4. The specific speed for a hydraulic turbine is usually taken either for fully open inlet gauge in at the sign head or at the point of maximum efficiency. Since the actual head on the turbine may fluctuate with labor flow, the sign head is usually selected as the weighted average net head when weighted on the basis of kilowatt hours generated. Sample number 1. What is the specific speed of the turbine having a brake power of 3,000 horsepower running at 520 RPM and a net head of 115 feet? The given P is an horsepower, 3,000 and 520 RPM, S sub n is equal to 115. So the specific speed is N, P exponent 1 half over S sub n 5 over 4 is 520 times 3,000 exponent 1 half over 115. 0.5/4 is 75.6. RPM is not actually a unit of Nth of S. Pag kinuha mo yung mga unit dito sa loob, horsepower dyan, so hindi yan equal sa RPM. Tinawag lang ng RPM kasi nga ang tawag dito sa tong quantity symbol na to, variable na to is specific speed. Okay? Ang specific speed talaga is dimensionless. Okay? Check nyo yung fluid machinery nyo kung ito tayo na definition ng specific speed. What are the types of hydraulic turbine? So, meron. A hydraulic turbine is a power unit that allows the transformation of potential energy of water into mechanical energy. It consists of a fixed distributor component with the mechanical function of channeling and regulating the incoming flow to the impeller and the hydraulic function of converting the water potential energy into kinetic energy. The mga nozzle. A mobile impeller component that is set in motion by water exiting the distributor with the task of delivering mechanical energy to the shaft on which it is mounted. The choice of suitable turbine is made by means of nomogram, into which the project data is loaded, available draft and water flow, allowing the identification of the most suitable type of turbine and its size and its in terms of power. So ito yung mga type. Pilton microturbine. This is an impulse hydraulic turbine which is suitable for facilities with high draft, up to a few hundred meters. It is very similar to the turbines used in larger plants and has a horizontal or vertical axis. This turbine has many advantages. One, it operates at atmospheric pressure. Two, it has a simple, robust build, is small, and provide a high level of performance. Number three, it has a relatively low number of revolution and can therefore be adapted to even very high water drop. Next, the turbo microturbine. This impulse hydraulic turbine is similar to the Pelton turbine and is suitable for drop of between 30 and 300 meters. It is recommended in situations with considerable variation in inflows of turbine water. Next type is the radial or cross-flow microturbines. These are suitable for facilities with low and medium drops from a very few meters up to 100 meters in a capacity between 20 and 1,000 liters per second approximately. They are used in low power plants. The advantages of this hydraulic turbine are similar to those of Pelton ones, except they have a lower level of performance. They are, however, easier to build and can also be adapted to lower drop. Next is the Francis mini turbine. This is a reaction hydraulic turbine for power with a lower limit of around 100 kilowatt, and this is why it is called a mini turbine. Advantages include a high speed of rotation suitable for small medium drop, used in open chamber facilities with very small drop, and the possibility of exploiting all the available drop right up the spillway. Disadvantages include its complex construction, issues surrounding sealing due to difference in pressure of the failure between upstream and downstream, competition, and due to the pressure of the diffuser, pressure in water due to high water level speed against the blades. Turbine speed now. Nearly all modern hydro units are directly connected to electrical generator that provide 25 or 6 cycle current. 40 cycle frequency is used in people-means and 50 cycle frequency is employed in some foreign countries. Sa atin po is 60. These generators must have an even number of poles. Yeah. For the speeds used per unit of even a few hundred horsepower, it is preferable that the number of poles be divisible by 4 for greater flexibility and generator design. Turbine speed are limited by the following equation in addition to the data of figure 1. The figure 1 is typical specific speed for turbine runner. Speed, specific speed. May speed ka, kapag may specific speed, so dito makukuha mo siya kung ano yung gagamitin mo type. So N is the N 120 F over P, where N is a turbine generator speed, F electrical frequency, cycle per second or hertz, P is the number of generator pools. Large generator may have a speed of 6 RPM. Speeds as low as 40 RPM have been considered. Most generators of more than a few thousand kilowatt capacity operate at speed of 300 RPM, although there are some exceptions. Example number 2. A 5,000 horsepower turbine is to be installed for a 50 feet head. Select typical speed for Kaplan or Francis speed for 60 cycle current. Given P is 5,000 horsepower, S of N is 50 feet, F is 60 cycles per second. Kaplan or Francis speed, required typical speed. Solution. From figure 1, the specific speed of 50 feet for Kaplan wheel should be about 111. 50, hanapin mo yung Kaplan, that is 111. Diba? Yan. 50, 50, tapos yan. Huwag nyo nang i-drawing to. Figure na yan, ha? Hali. Hilig nyo mag-drawing. Pati ito, dinodrawing nyo. Sinabi lang may figure, pati ito, drawing nyo na. While Francis wheel, it should approximate 90. So 50, Francis wheel, and yan. 50, nagulig na ako. 90 daw, 90, o tama 90, yan. Now, for the speed of Kaplan turbine, N is equal to N sub S times H sub N exponent 5 over bar over P exponent 1 half is 111 times 50 exponent 5 over 4 over 5,000 exponent 1 half is 208.7. Next, the nearest generator speed from equation 4. So using the number of poles is 4. So N 120 F over P. So P is equal to 120 times 60 over 208.7 is 34.5. The nearest divisible by 4 is 36. So N is equal to 120 times 60 over 36 is equal to 200 RPM. The next ano yan is 32. 32 pa malapit, di ba? 32 to 36, that is between 32. So 34.5 minus 32 is 2.5. 36 minus 34.5, ilan? 1.5. So doon ka sa nearest. For the speed of Kaplan turbine, so ito. Next, N is equal to N sub S, H sub S 0.5 over 4 over 6.1 up is 90 times 50 exponent 5 over 4 over 5,000 exponent 1 up is 169.2. Next, the nearest generator speed from the equation 4, we have number of poles divisible by 4. So N is equal to 120 times 60 over 169.2 is 42.6. So use 44, N is equal to 120 times 60 over 4. The 4 is 163.6. Okay. Next, cavitation. The phenomenon of cavitation was defined as the implosion of vapor bubbles in liquid. Kadalasan nag-istro na yan, pump, plumbing, sprinkler, so mechanical, o basta may pump, nalimutan na yung cavitation. So these bubbles are formed by the passing of some of liquid into vapor caused by a reduction of the liquid pressure below the vapor pressure. When the liquid pressure is then increased above vapor pressure, the bubbles include with a release of large amount of energy. Some small amount of this energy is dissipated as sound. So the remaining energy causes vibration of the equipment and also tears away part of the surface of the boundary metal. When cavitation occurs in pumps and turbines, the metal becomes pitted or honeycomb. The efficiency and maximum power of a unit may be badly impaired by severe cavitation. Cavitation is most likely to occur on the outer edge of the back of branches and propeller blades and on the band of branches runner. Because propeller runners operate at high specific speed, they must be set lower to avoid cavitation. Cavitation on the runner can be controlled by the elevation of the runner above or below tailwater level. Other points at which cavitation can occur are on duct tubes, at sharp corners or section, and on the needle and deflector of impulse turbine. Impulse runner may encounter cavitation on the back edge of the bucket tip. Tests of model runners are the best reliable means of detecting cavitation. From this test, the proper elevation of the bottom of Francis wheel or center line of the Francis wheel can be determined. This elevation is one of the most important determination that must be determined for the plant and that will involve the use of sigma function. However, preliminary calculation may be made by establishing the minimum permissible pressure at the wheels as being equal to the vapor pressure, so VAP. Some manufacturers use an arbitrary value of zero point 0.6 feet for HVAC. This will be equal to the barometric pressure less the pressure due to elevation of the wheel above the tailwater, H of E, less the velocity of head at the wheel outlet, H of V, all expressed in feet of matter. Or the velocity head at the running outlet is proportional to the square of velocity at this point. In turn, the velocity is proportional to the volume of water flowing. So that velocity head is proportional to the square of flow. But the square of flow is proportional to the net head and so on. Therefore, the velocity head is proportional to the net head. Then taking sigma as the constant of proportionality, S sub b is equal to sigma Sn. Combining the above equation is sigma is equal to h sub b minus h sub e minus h sub b divided by h sub b, or h sub b is equal to h sub b minus h sub b minus sigma s sub n. The real dictum. If the runner is above the water level, h sub b is positive. If the runner is below the tailwater, h sub b is negative. Values of the vapor pressure may be obtained from steam level and converted into feet of water for summing water temperature. Barometric pressure is that existing at the plant point elevation and not the barometer pressure corrected to the sea level. For most purposes, it is necessary to assume the barometric pressure as 34 feet, less than 1.13 for each 1,000 square feet, 1,000 feet elevation in elevation above sea level. Now, the constant of proportionality, sigma, is called the cavitation factor and is assumed to be constant for all heads in a given runner and for all proportionally similar runner. Actually, sigma varies with gate and blade angle. So, yeah. This is constant table. The barometric pressure is values of vapor pressure may be obtained from steam table and converted into feet of water for summer water temperature. Barometric pressure is that existing at the plant elevation and not barometric specific to sea level. Okay, for most purposes, it is satisfactory to assume the barometric pressure as 24 feet of water less 1.13 feet for each 1,000 feet. It is elevation above sea level. So, ito important dito. Sa fountain, important rin ito. Itong note na to. Saka yung topic in advance, meron din sa ganito. Hindi ka tinigin ng table. So, ito gamitin natin. The constant of proportionality is sigma is called the capitation factor and is assumed to be constant for all. Ay, nabasa ko ito. So, the minimum, actually, sigma varies na. The minimum sigma is necessary to prevent cavitation is the critical sigma. The operating sigma is the value at which the turbine actually operates and should not exceed the critical sigma by an ample region to prevent cavitation due to unforeseeable variation in equipment manufactured and operated conditions. The approximate value of sigma suitable for the solution of problem may be obtained from the following equation. So for propeller turbine, sigma is equal to n sub s squared over 15,000 minus 0.2. For Francis turbine, sigma is equal to n sub s squared over 15,000. Some metals are subject to the fitting effect of cavitation than others, porous materials being the most susceptible. Cast iron, which is used for the small low-head turbine of one type, is the most susceptible to cavitation fitting. Some bronze having about one-third the rating of fitting of cast iron, while cast carbon steel exhibit only one-eighth the rate of the fitting of cast iron. Cast stainless steel, 18% chromium, 8% nickel. Aluminum bronze has 1/16 the rate of cast iron. Most standards today are made of cast iron steel, and many are protected with a weld or layer of stainless steel over the areas more likely to be subjected to fitting due to cavitation. Other runners will be provided with stainless steel exit or blade segments welded in place. Example number 3. So for 5,000 horsepower, 350 feet, 200 RPM Kaplan unit of the preceding example, determine the elevation of the propeller central lines for a 3,000 feet elevation and 80 Fahrenheit. Given P is 5,000 horsepower, H sub n is 50 feet, and is 200 horsepower, elevation is 3,000 feet, required elevation of propeller central line. So P. Yeah, H sub P. Solution, so specific speed, kunin mo. Itong pamira natin, yan, pinapod mo na. H sub B is equal to H sub B minus H sub up minus H sub up. So, makuha mo yan sa elevation. So, H sub S equal to M2 exponent 1 up over H sub S point 5 over 4. H sub S equal to 200 times 5,000 exponent 1 up over 50 exponent 5 over 4 is 106.4. So, sigma is equal to H sub S squared over 15,000 minus 0.2. Sigma is equal to 106.4 squared over 15,000 minus 0.2 is 0.555. Then H sub E is equal to H sub B minus H sub up minus sigma H sub N. So the barometric pressure is H sub B, 34 minus 1.13 over 1,000 times 3,000 is 30.6 feet. Ito yung H sub B mo. Diba? Ayan, binagit dito yun. Ayan. So at 80 Fahrenheit, vapor pressure is 0.507 psi and the specific volume of water is 0.01607 cubic feet per pound. Pati kinuha yung specific volume ng water. Kasi sa water tayo, di ba? So, para makuha mo yung head and water. So, this is, the head is, and vapor is PB is equal to 0.01207 cubic feet per pound times 0.507 psi times 144 square inches divided by square foot is 1.70 feet. So, H sub B is equal to 30.6 minus 1.17 minus 0.555 plus 50 is 1.68 feet. Since this is a plus value, the center line of the runner should be set at least 1.68 feet above the minimum fill water level that can occur when a turbine is developing 5,000 horsepower. Okay? This is now the end of this topic for hydroelectric power plant.